All right. So this is now in recording. You cannot see it, because the Zoom window is on my side, on the other side of what you guys are seeing. And I'm going to share screen. So this way, it's going to record what you're actually seeing, which is desktop 2. And it should be recording right now. Cool. All right. All right. So I'm going to start the class officially. It is important to keep updated with all the announcements. So when I send something out, you should get a copy as an email. So be sure to read it, like I would say within a day, within 24 hours would be good. I'm uploading, I'm downloading all the Zoom recording and then re-uploading to YouTube because YouTube has a pretty good closed captioning capability. Even compared to Zoom, I would say YouTube is superior. I'm not going to tell you some examples, that I looked at the closed captioning from Zoom, and it was, I would just say it's inappropriate, okay? So I cannot repeat that in a class. But, YouTube is really good. I mean, it missed occasionally certain words, even with my accents. So it's actually doing a pretty decent job. Now, the other thing about YouTube is it's great for people who may be struggling with English, especially with my English. Okay, because with YouTube, once it is closed captioned, you can actually have the closed caption to translate to a different language. So I'm just using Chinese as an example. I actually checked it out. So I was watching my own video, which is recorded in English, and the English closed captioning is like, wow, this is okay. It's pretty good. Capture everything that needs to be captured. And then I went to that option and translate the closed captioning to Chinese, and it was still okay. It was really hard for me to follow because the technical terms I'm not familiar with. But when I actually read, slowly, it's like, yeah, that's how I would translate it. But I'm not familiar with the technical terms of a lot of computer science stuff. The normal conversational stuff, yeah, but not so much in terms of a technical content. So that's an alternative, for people who want to kind of be able to translate the content into a different language because it makes it easier to absorb the content. I do that a lot because I watch a Japanese anime and I only watch the sub version, okay? Because the dub version is usually like, why would they choose a voice like that? Isn't that the same voice as blah, blah, and so on, I was just recently watching how the voice actress of Ash in the Pokemon series basically did, there were 2 or 3, main people doing the voiceover for Ash Ketchum, and it was just kind of interesting. Obviously, totally not related to this class. All right, so we're going to get started here. And I'm going to close off my Outlook tab here because otherwise it's just going to ding me, whenever I get a new message. So what we'll do today, first thing is I am giving you a homework assignment. But before anyone goes to do it and then say, oh, this is easy, I'm just going to submit right now. Let me go there first and talk about it a little bit before you get started with that homework assignment. So the homework assignment is set theory. That's how you would see it. And the first thing you need to make sure that you understand is you only have one attempt. Because many of you took my CISP440 class, and all of the labs are, oh, you can retry as many times as you want, and it gives the highest score. Not with this one, okay? This is a one-shot deal, and you won't know the answer. The quiz does not disclose the answer until the due date. All right? Which is basically my way of saying, okay, try to do this on your own as much as possible. Clear up all the concepts so that you're 100% confident with the answer before you click submit. All right. You have plenty of time, at least I think it is plenty of time because it's due next Wednesday, right before the class starts. So you do have quite a bit of time to work on it, including one additional class meeting on next Monday before it's due on Wednesday. So I would suggest that all of you get started with this one as early as possible. Okay, read all the questions and read all the material related to those questions. Go back to your notes, review your notes. Okay, just go over the material until you're saying, okay, I know for sure this is the answer for that question. Because if you're not sure, that means you might need to go back and clarify some of those concepts. I do have office hours, so come to my office hours if you do have any questions, so that I can help you, with the clarifications, or I can make some changes to my notes as well if it is like, oh yeah, that's just a poor way of describing it. Then I can go back and change that. All right, so are there any questions about the homework assignment? You're good? All right, excellent. All right, so we are going to start off with, well, let me just kind of go back and see if you guys have any questions about the material that we have already talked about. And I think we are not quite entirely done with set theory yet, so we still have to just a little bit more to finish up today. So that's what we're going to do first, today, and then we're going to move on to quantifiers. I believe the last topic that we talked about was union as a set operator. Is that correct? Okay. So that means today we can look into difference as an operator. It looks like subtraction. So if A is a set and B is also a set, then A minus B, I'm going to say minus because that's what the operator looks like. So A minus B is going to be a set where the membership of that particular set is qualified by this statement over here, or by this expression over here. This expression has an and, just like with intersection. But what is different about this one is there's a negation to E being a member of B. So if you were to translate that into English, which is vague and not exactly precise, this is basically saying A minus B is a set. The elements of this particular set has to be found in A, but it cannot be found in B. That's basically what it's saying. Are we good so far? Everything in A that cannot be found in B. All right. So as in the previous class, I'm going to give you guys a few live exercises. Okay, so we're going to do let's try A, B, C minus 1, 2, 3. All right, so what is the answer of this particular expression? ABC. It's just ABC. Very good. Okay, so we'll say this is just A, B, C. Excellent. Let's try another one. So this time we'll try A, B, C. Okay, so minus, we'll make this an easier one. 1, 2, oops, 1, 2, C. What would be the answer in this case? A and B. Yep. So A, B is in the result. Do we have any questions? Because I want to give you guys the time to absorb this and be able to say, okay, wait, I'm not quite sure why that is the case. So do we have any questions about these two examples? Okay. All right, let's try something else. Let's try the empty set minus the set that has 1, 2, 3. So what is that going to be? It'll be the empty set because it's everything in the empty set, but not in the set that has 1, 2, and 3. Well, what is in the empty set? Nothing. So the result is going to be a set that also has nothing. All right, very good. That's about it. I mean, okay, well, the last one. Okay, I know you guys will get this one just fine. So we're going to have A, B, C as a set minus A, B, C. So a set. So what is the result of this one? The empty set, because everything in A is also found in B, so this is going to give us the empty set. All right, so I think if you're comfortable with all four examples, then I think you got the concept. Okay, yep.
Each set has a subset of empty set, right?
Say again?
Each set has a subset of empty set.
Each set, yes, but we haven't talked about the subset concept yet. So we'll wait a little bit until we get to that point. Have we talked about subset? I don't remember. I don't think so.
We didn't? Oh,
Yeah, that means you must have read ahead of time, or you have some concept of the set notations from somewhere before. But that's good. Okay, yeah, we'll get to that too.
okay.
Yeah, so when we get to the empty set, discussion, you can kind of come back and mention this one. Okay. All right. Excellent. So we'll go back to the notes here, and then we move on to the next operator. So the next operator, it looks like a times, looks like a cross, looks like the lowercase x. It is called the Cartesian product operator. So the Cartesian product operator is really it's kind of like a cross product in linear algebra. Okay. It does kind of the same thing, except it doesn't give you the product as in multiplication. It gives you a two tuple as a result. And that's why with this particular operator, there is a little bit more explanation as opposed to the previous one. So I need to first explain what is a two tuple. So a two tuple xy is, xy in parentheses is called a two tuple. The best way for you to look at a tuple is to basically say a tuple is a vector, or a tuple is an array. So that means the position of a value within a tuple is significant. And on top of that, you can have the same value repeated multiple times within a tuple. Just like you can have an array of values, and some of those values can be identical. So are we doing okay so far with the concept of a tuple? I mean, using today's terminology or symbology, most scripting languages, they would use square brackets to enclose the content of a list, which is also can be considered a tuple. So if you know JavaScript, or if you know Python, you would be using square brackets instead of parentheses. But in this class, because this is more or less a math class, so we're using parentheses instead of square brackets. I'm just using the square brackets as an example, so that for those of you who know a scripting language, you know what it is equivalent to. Are we doing okay so far with all of those things that I just said, about a tuple? Yes.
I'll give an example
of
what this.
So this xy here is already a tuple. Where the mouse cursor is. This is a tuple. It's just that the first value within the tuple, which we would normally associate with index 0, is a quantity or value that we know as x, and then the second one, which is an index 1, is known as y. Is that sufficient as an example? I mean, it's basically an array or a list or a vector. All of those are somewhat equivalent from the perspective of this class. Yeah.
So is it similar to the intersection operator, just being ordered and having multiple?
Not quite. Okay, not quite. This is not the intersection operator. Let me just kind of finish reading this particular paragraph, and you guys can see if there are any additional questions. A tuple is a container, just like an array is, but it is ordered and it may have duplicate values. As a result, in our definition of the Cartesian product, each element of the Cartesian product is a two tuple. Furthermore, the first item of each tuple must be an element of the first set, in this case, set A, and the second item of each tuple must be an element of the second set B, which is also from this particular notation. All right, so I think it is best to give you an example, okay? Because once you see the example, you go like, oh, so that's what it means, okay? So let me present the example first, and then you guys can then ask me, specific questions once I have the examples. So we have the first set here being AB. And then, okay, let me close it first, so this video doesn't look too awkward from your side. So now we have times 1, 2, okay. All right, so I'm just going to describe the outcome, of the result of this expression, and then you guys can go like, oh, so that's what it means, okay. So this becomes the result is also a set. The set basically consists of every single way you can pair up an element from the left-hand side and an element on the right-hand side. So it's A1, A2, and then we have B1 and B2 as tuples. So there are 4 elements in the result. Each element in the result corresponds to picking up one value from the left-hand side of the operator and picking up another element from the right-hand side of the operator. Yep,
It's kind of like FOIL.
it's kind of like FOIL, yes. Or cross product in linear algebra. Is that okay? Does everybody understand how the Cartesian product operator works? I'll give you guys a little bit of time because this is one that is a little bit quite different from the other operators that we have talked about so far.
So one set is empty, then the tuple is empty, and what's this?
That's a good question. Okay, that's a very good question. So let me give you guys another example here. And this time we have A, B. Let me close that first. Times just the set is just 1 in it. So what do you think is going to be the answer in this case? A1, B1, that's right. Okay, so the answer is just A1, B1, just like that. Basically, it is looking at all the possible ways to pair up elements from the left-hand side and the elements of the right-hand side. Are we doing okay so far? Okay, all right. All right, so let me throw a wrench into this whole thing because that's what I'm very good at. So this time I'm going to have AB just as usual times the empty set of all the things. I'm going to try to find out the Cartesian product of something that is non-empty with the empty set. So what do you think is the result of this particular example? The empty set, exactly. There's nothing to pair up. So as a result, there is nothing. Are we still doing okay so far with the Cartesian product notation? Okay, all right. Yeah.
Is there anything you can multiply it by to make the answer easy still?
No, because the result of a Cartesian product should always end up with the elements looking like 2 tuples. They always have to be 2 tuples because the first item of the 2 tuple has to come from the left-hand side, and then the second item of the 2 tuple has to come from the right-hand side. So you cannot have single, non-tuple, values within the result of applying the Cartesian product.
A and B were reversed, completely different.
Yeah, because remember, everything that is directly inside the curly braces is in a set. And in a set, there is no inherent order. So I can just say the result of this one here is B1, A1, it would have been just as valid as an answer as this. There's no intrinsic ordering within a set.
The tuple itself has to be.
Within a tuple, it is important, yes. So within a tuple, A1 as a 2 tuple and 1A as a 2 tuple, they are 2 different 2 tuples. They would not be considered the same. So once again, the best way to look at a tuple is to look at it as an array. I mean, that's the closest concept, and I think it's pretty much the same thing as an array. So a two tuple is basically an array with two elements. Are we good so far? All right. Are we good? All right. So the concept of a Cartesian product is going to be quite important later on when we talk about the concept of a function and also the concept of a relation. Yes, go ahead.
You said that two tuple is like an array with two elements.
A two tuple is kind of the same thing as an array of two elements. Yes.
I just want to know if we look at it as two elements or like a 2D array,
As two elements or two.
D array, or two-dimensional array, sorry.
No, it is not a two-dimensional array.
It's just two.
Yes. It's an array with two elements.
Don't we have pair in space?
Don't we have?
Pair that has one and two. Dynamics.
Don't we have
Pair,
pair?
Pair container.
it's like an array, but it only has try.
You can look at a pair as a two tuple. But there's no intrinsic meaning of the first item in the pair versus the second item in the pair. Because when you talk about a pair, I think you're implicitly saying it is a key value pair. So in the case of a key value pair, there's a implied meaning to the first versus the second item in the pair, because the first one is the key, which means it has to be unique within the collection. And then the second thing is just the value, so it can be anything. But in this case, there's no intrinsic interpretation of what is the first item of the two tuple and what is the second item in the two tuple. The only thing we need to know is the first item of the two tuple has to come from the left-hand side of the Cartesian product operator, and then the second item in the two tuple has to come from the right-hand side of the Cartesian product operator. But that's the only thing we need to know. So does that kind of help clarify the answer to the questions? Okay. All right. I'm glad you guys are asking all these questions that I did not think about, because it did not occur to me that this concept is relating to a pair, and then the most common use when we say a pair is a key value pair. So the answer is that there's no intrinsic meaning to what is on the left-hand side versus what is on the right-hand side. Any other questions? Okay, no other questions? So we're going to go back and look at the description, because we are basically learning what a Cartesian product operator is by example, which is fine. I mean, that's a great way of learning things. But once we look at the examples, it is always good to be able to look at an abstract and precise description of the operator. So instead of describing this to another person or to yourself and say, okay, the only way I know how to describe this is through examples, we want to be able to find a language that can express the same thing. And the language to express this is the result of A Cartesian product B is once again a set. What is in a set? Everything in the set is a two tuple with x, y, in it. So x is a variable, y is a variable. The only thing we know up to this point is everything in the result is a set, and everything in the set is a two tuple. What about a two tuple? Do we have constraints about this particular two tuple? Yes. So the constraint is x has to be an element of A and y has to be an element in B. So that is how we use the language that we have talked about, or the notations that we have talked about from the earlier parts of the same module, and we reapply those in order to have a precise and also very concise way to describe what is the Cartesian product operator. Are we doing okay so far with this? Can you guys all kind of link this notation of how I define the Cartesian product operator, and how we can relate that to the notation that we have described from the previous part of this module? Because that connection is understanding. Okay, understanding is not understanding every single word in the sentence, meaning that you recognize. Okay, there's a difference between recognition versus understanding. Understanding is making connections. you're making a connection from one particular notation or expression here to things that you have learned already. That connection is the basis of understanding. All right. So what is a deep understanding? Go ahead.
I was
Sorry.
gonna ask, does the Cartesian product operator also work like, is there like a 3 tuple? Can we multiply those?
That's a very interesting question because you can apply another Cartesian product out of the result of a Cartesian product. So you can basically chain Cartesian products to make longer and longer tuples. And it's a very useful concept because it does allow you to look at all possible ways of pairing things. So it is a very powerful and useful concept. I use it a lot in many of my scripts to generate variations of questions in exams, which you guys will experience. Any other questions? So I'm not only describing, just the Cartesian product operator, I'm also trying to make sure that we are relating this notation to things that we have talked about already. And it is super important that you feel comfortable with the notations at this point. Yep, go ahead.
So what are you saying? You would how to interpret that?
This whole thing?
Yes.
Okay, I'm going to mention something that is going to be quite annoying to many people, which is, what do you think? So how do you approach this? Okay, if you are a student and you're looking at this and you're going like, this is new to me. What does it mean? Okay, so what do? You recognize the components and then you say, have I seen this before? Is this notation defined? So the first thing is the notation in parentheses x1, that is new. And that's why we have an entire paragraph here to describe what is a two-tuple. That is new to us. But the notation of using curly braces, that's not new. We talked about that already. Okay, because we use the curly braces or just braces to denote whatever is inside a set. So we're talking about a set here. The bar notation, we talked about that too. There's something to the left-hand side and something to the right-hand side of the bar. But whatever is to the left-hand side of the bar is saying every element of this set looks like this. Okay, whereas before they're just a single thing, now we're putting that extra constraint that every element in this particular set has to be a two-tuple. What about the thing to the right-hand side of the bar? Okay, this is from here to here. This is why the screen recording can only help so much because I tend to point to the projector, instead of using a mouse pointer because, well, I suppose I can try to do this too using the mouse pointer. So whatever is to the right-hand side of the bar is a constraint. It is a condition. It specifies, well, we don't want every two-tuple to be in this set. The two tuples that can be and should be in this set has to make this as an expression tree. So those things are the things that we have talked about already. So as I said earlier, it is important for us to recognize things in something in the new thing that we are talking about and be able to relate that to things that we have learned already. But Tech, you only talked about it in the previous lecture. Yes, I have a tendency only to say things once. So it is really important for you guys to review the material as much as you can so that you feel comfortable with things that we have talked about and introduced already. Taking notes is important, okay? At least to some people, it is important because instead of just reading everything that I write, you're gonna, oh, okay, this is how I would explain this. The way Tech explains this really sucks. I have a better way to do it. And this is the way I'm gonna explain it to myself. That is what the notes, that's why you take notes, okay? Because otherwise, everything is being recorded. I mean, there's no need to frantically copy stuff on the screen. Are we doing okay so far? All right. So I'm hoping that I'm not only teaching the content, the knowledge of this class, but I'm also kind of expressing what I think is understanding, what I think is an effective way of taking a class, and so on. All right. Any other questions? Questions? Okay, all right, so we shall move on to the concept of a subset, okay, which is what you referred to a little bit earlier. So this is one way to define a subset using everything that we have learned already. This side here is new, but everything else is not. I know we just learned the minus, symbol in today's class, but we'll go ahead and see if, we can make something out of this. So A is a subset of B, okay, so this will, it's like a U, but rotated 90 degrees clockwise is called subset of. You have to remember there's a bar under it too. Okay, so A is a subset of B if and only if A minus B, using the definition of set subtraction, is an empty set. That's it. Okay, so what exactly does it mean? The other way to say this is everything in B is in A. So I'm gonna pause here and see if you guys can equate what I said in English. Everything that is in B can also be found in A. It's the same thing as saying everything in A but not in B is nothing. Does that make sense to you? So I'll give you guys a moment to kind of let it sink in. Some people feel comfortable with that explanation, and some people may need a little bit more time to think about it.
It's only one way, not the other way.
Only one way, yes.
So if like A is a subset of B, B could potentially have stuff that is not in A, correct?
That is correct.
Okay, just wanted to double check.
Yeah, B does not have to be quote unquote a smaller set. Well, actually, take it back. Say that one more time.
So everything that is in A is in B, but not everything in B will also be found in A. B could have some items that aren't in A, but it could still be A could still be a subset if like everything in A is in B.
That would be a problem. So that means this notation will not work. Okay, so that's you're hitting on something that makes me think that this is not the right definition. There's something else that it needs in order to define the subset. Okay, so I'm going to take roll first. If you have a mobile device, a phone or a cell phone, you're signed into Canvas, and I am going to get to that part. So very good. I like what you just said, because you might have spotted a mistake in my notes. And that's good. All right, so let's take row first, and this is the row taking activity, and I'm going to change something just so that it matches what we are talking about. So the access code was what password, because I just thought that's a pretty cool password. And I'm going to change it to tag is wrong, which is true. So I don't have a problem admitting that I'm wrong. And it's going to be
Yeah.
tag uppercase is uppercase wrong. It's camel case, and which you use in C++ and Java programming. All right, so I'm going to give you guys quite a bit of time. Let's say 11:55 p.m. So you have that much time, and save and publish. And it's going to repeat the access code again. Is tag is wrong, uppercase I and uppercase W. So I'm going to wait a little bit here. You can also use this as an opportunity to take a short break. So does anyone need more time with the row taking thing? Okay, well, go ahead. You guys take your time, and I'm going to do something on the side to fix my notes. So I'm going to fix it while you guys are working. Because I know exactly how to fix it now. It is 280.
You're the one who's saying weird things. I know what said. You say her name should change. No. I've heard. Yeah, maybe from weirdos who say things that nobody says. Like how much time. So I'm gonna be on yanking the chain. Yeah, but if you don't.
I'm guessing most of you are done.
Nobody says, nobody says anything wrong. And because you said it and nobody said it, therefore. But you're your property, you're nobody. Reckon. Oh, but-
All right.
Also be. There's not sure if it's-
That was a nice little break. Do you know that each person is at least equivalent in terms of thermal output as a 200-watt heater? And that's with us, sleeping at rest, not really doing anything. So with anything of, like active, thinking or, that's at least like 300 watts. And we have about 40 people. So, 300 times 40, that's a lot of energy. That's a lot of your thermal energy.
Really?
Yeah, yep. And that's why the room actually does heat up because of, a lot of people in the classroom. You can think of it this way. Every 10 people is equivalent to a hair dryer. And that's every 10, so we have about 4 hair dryers worth of thermal output in this room. And it's constant because you don't turn on the hair dryer like for an hour. This is constant. All right, so I just made a correction. This is uncorrected. So what you said is right, okay? What I described in English of everything in B, must be in A. But it does not include things, that is this expression, okay? The meaning, the English description is right, but this is not correct. Because if you want to make A minus B equal to the empty set, they just don't have to share anything. So A can be, in an example that we have already looked at, A can be ABC, B can be 1, 2, 3. In that case, A minus B does equal to the empty set. But what I claimed in English, which is everything in B must be found in A, was not true. So I did make a mistake here. So I just made the correction. So let's go ahead and take a look at the corrected version, which is the same thing, but with a. Okay, let me go back to that section. But with an extra requirement that B minus A equals to B. Okay, so what does B minus B equals to B? This is the only thing added within a conjunction to what we had originally. So what does it mean when we say B minus A equals to B? Everything in B. Oh, this is wrong too. Okay, wait. Okay, let me. So B minus A equals to B. That means. Oh, okay, I got this wrong again. It should not be the minus symbol. Should be a cap. There we go. So let me do it one more time. I'm gonna release this. So the nice thing is, when I make corrections, it is also corrected. It's the correction is made to the link document from Canvas. So if you refresh your document, it would be correct. All right, so we'll do it one more time. Set operators. Oh, okay, almost there. There we go. So the correction is A minus B is an empty set, and then the second requirement is A intersecting with B has to be B itself. So with these two, okay, with the conjunction, now it is defined properly. So what you said earlier is a great example of basically questioning, okay, you don't take everything that tag you're saying, for granted, it's you go like, does that make sense? How can I check that? So what went through your mind was probably using an example, right? Did you use an example in your head to kind of notice that, this doesn't seem to make sense?
Yeah, like at first I went through like the concept of it, and then I was like, what could possibly like kind of like
Mhm.
throw a wrench in this?
Right. Very good. All right. So that's a very good example of, just not only paying attention in class, but also using critical thinking to question, does that make sense? Okay, based on what I have learned already, is the mathematical notation matching what subset L is supposed to express? So very good. Good job. Kudos. All right. So this one is the correct one. Okay. So in this case, we have a conjunction. The conjunction, the left-hand side of the conjunction is still saying A minus B equals to an empty set. So what that is, saying is, everything in A that is not in B, there's nothing like that. There's nothing that is in A but not in B. The second one means everything that is in B, they also must be in A. Is that okay? So we're going to look at some examples and see if this is true. Okay, so we're going to run through a few examples. So we'll go ahead and go through some examples. And in this case, I'm just going to say what is in A and what is in B. So in the first one, A has A, B, C, and then B is just A, B. So we're going to go through those two, the expression. So we're going to say, what is A minus B in this case? And I should probably make this a little bit more because I'm going to separate the multiple parts. So in this example, A is ABC, B is just AB. What is A minus B? C. It is C.
I think you're doing should be minus.
B minus A, right? But it doesn't hurt to also specify this having just C in it. And then we ask the other question, which is what is B? B minus A, and B minus A is an empty set. Okay, so let's double check that. Okay, does that make sense to you? What is in A but not in B? Let's just see. What is in A? What is in B but not in A? Everything in B is in A, so B minus A is an empty set. Okay. And then we check the other one, okay? Because remember, I'm adding one extra requirement. And the extra requirement is what is A intersecting with B, which is a cap. So what do I put here? So A intersecting with B is asking something that is in A and also in B. Yep, lowercase a and lowercase b, which is the same thing as just b itself. So let me read my own notes here.
This should be intersect B should be A.
So that should be b.
Intersect B should be A.
Hmm?
Intersect B should be A because subset is A not B. In the definition. A is subset of B, right? So A intersect B should be A, not B. Because B might have extra elements which is not in A. A is a
No,
subset,
b
not A.
cannot. Oh, right. Okay, I got it flipped. One more fix. All right, so I do apologize for this, because this is not good. because B is the bigger one, you're correct. A is a subset of B, so let me go back to the notes first, because I fixed that already. So we just want to make sure that we do not get this part wrong. All right, so A is the smaller set, B is the one that contains, that can potentially have extra elements. So in this case, everything in A but not in B has to be empty. That is good. And when we make an intersection, it should be the set, the smaller set, which is A. So that is correct. And in the example that I was just going through, it is B, but it is not A. Okay, so I'm gonna say A. So that's why in this case, A is not a subset of B. So I'm gonna say, I will make it very clear. Okay, A subset equal B is false. Is that okay? All right. So what if we reverse that? Okay, so I'm gonna use this as a starting point, and we just reverse that. So A is AB and then B is ABC. We're gonna rework all the ones that are relevant, which is A minus B and also A intersecting B. All right. So what is A minus B? Everything that is in A but not in B. You guys can focus on, I need to scroll up a little bit. There you go. So your focus should be here. What is in A but not in B? No, the empty set is right? Because A has got lowercase a and lowercase b, but all of those can be found in B. As a result, A minus B is indeed the empty set. Okay. What about the intersection? The intersection of these two continues to be just the set with AB in it. But in this case, it is identical to set A and not set B. Is that okay? Because if we're looking at the intersections, we're looking for the elements that can be found in both set A and set B. So set A has AB, set B also has AB. It has an extra C in it, but if you're looking for the overlap, it only has AB, which turns out to be the same as just set A. So both of those requirements are met. And as a result, in this case, I can now say A is a subset of B is true. Is that okay? Yep.
For the first example, though, B is a subset of A is true, correct?
That is correct.
Okay.
Yeah, it's just reversed, right? All right. So now I'm going to give you another example, okay, which is kind of still based on all this stuff here. So now I'm going to give you ABC is A, and ABC is also in B. So A and B are the same. So the question is a set its own subset? Okay. So we'll double check, right? And so we are going to use A minus B. We will evaluate that one. And also A intersecting with B, we'll evaluate that one too. All right, so don't trust the right-hand side of the equality. We want to work it out. So everything in A but not in B. What is in A but not in B in the third example? Nothing, right? Because set A has ABC, set B also has ABC. So A minus B is really the empty set. There's nothing that is in A but not in B. Okay. What about the intersection? The intersection of A and B consists of is a set consisting of elements that can be found in both of the sets. In this case, they are the same. So the intersection is really just ABC itself. So I need to make a slight adjustment here to also include element C in the intersection, but nonetheless, it is the same thing as set A itself. So this equality here is still holding. But remember, these two are the only requirements inside the conjunction in order to qualify that A is a subset of B. So as a result, in this particular case, okay, I can be lazy. just by copying and pasting it. So in this case, even though set A and B are the same, A is a subset of B is still true. So every set is a subset of itself. We do okay? Now, you mentioned something earlier, which is the empty set, right? So how does an empty set relate to subset of as an operator? So we'll go ahead and take a look. So in this case, A is going to be the empty set, B is going to be ABC. So we want to reevaluate, the conditions that we have to evaluate. So we'll start with A minus B. So in this case, when A is empty, B has ABC. What is in A but not in B? Nothing. Because A has nothing to begin with. So when I ask what is in A, and I don't even have to finish the sentence because there's nothing in A. Does that make sense? Okay. What about the second condition? A intersecting with B. So if A is empty and I'm looking for things that are in both set A and set B, there's nothing. Because set A itself is empty to begin with. And if you ask me what is in A, and once again, I don't even care the rest of the sentence because there's nothing in A to begin with. As a result, the intersection of A and B is also just the empty set, which is what A really is. So once again, we're meeting both of those requirements. And as a result, A is a subset of B is true. So are we doing okay so far? And I do apologize for the confusion or earlier. We good? All right, so we'll go take a look at one example where the subset is not true, okay? And it's not going to be trivial. So we'll go look at A, B, D in this case. So they have the same number of elements. They do have some overlap, but yet one is not a subset of the other. So once again, we're going to reevaluate the two conditions that we need to evaluate. So in this case, what is A minus B? Oh, you cannot see it because I need to scroll again. So we are looking at this example. A has the elements of ABD, B has the elements of ABC. What is in A but not in B? Aha. So that means this is not the same as an empty set. We're failing one of the two conditions in the conjunction array. Is that okay? All right. So that means, I don't really need to know the second one, because if you're failing one of the two sides of a conjunction, you're failing the conjunction itself. So at this point, I can already make the conclusion that A is a subset of B is false. Is that okay? Let's go through one more example where the answer is not true, okay? So we'll take a look at this one, which is 1, 2, 3. 1, 2, 3. So A has 1, 2, 3, B has ABC, and we want to once again evaluate the subtraction. So what is the subtraction this time? What is in A but not in B? Everything in A, right? Okay, so in theory, we can stop right now and say, it's failing one side of the conjunction already, so the conjunction itself has to be false. I don't need to evaluate the other one. But if you were to evaluate the other one, you would also find that the intersection rule is also broken in this case. So if you look at the intersection, so we want to look at A cap and B this time. What is the intersection? Nothing, right? It's an empty set. But the empty set is not the same thing as set A. In other words, in the conjunction, we're failing both sides of the conjunction. We don't have to, but I just want to show you that it is failing both sides of the conjunction, and as a result, A is a subset of B is false. All right. Are we doing okay so far? All right. So the next thing we want to talk about is a proper subset of. So this symbol here looks very close to this symbol here, except it doesn't have an underline. So it is basically a proper subset of. So in this case, A is a subset of B, if and only if A is a subset of B, and B minus A is not the empty set. In other words, you need to have something that is in B, but not in A. Is that okay? Yep.
So they can't be exactly the same on those
They
sides.
cannot be exactly the same. And the only way they cannot be exactly the same is B needs to contain some extra elements, at least one. Yep. So the way you can look at a proper subset of is B, in this case, needs to have extra elements, or at least, I should say, at least one extra element. It can be a lot, but it needs to be at least one. All right, very good. And the last part here, okay, I think I need to maximize it. There we go. So the last one here, which I think the people in the back may have some problem reading, is the bar notation is asking the number of elements in a set, which is also called the cardinality of a set. So I'm referring to the last paragraph here. Many times we're interested in the number of elements in a set. The notation bar x bar is called the cardinality of X, which is essentially the number of elements in X. So, and there's an example of your bar inside there's a set of 2, 4, 6, 8. So in that case, the number of elements of that particular set is 4. Yep. I can't actually scroll up because it's the last thing in the browser. What I can do is to resize it so that it doesn't end all the way at the bottom of the screen. Let's see, resize. There we go. And now if I scroll up, you can see it. One of the things that I told the architect, who designed and this entire building was, the placement of the projector needs to be, placed so that people in the back can see the entire, projection screen. And obviously, they did not listen. I also asked for lights here not being placed right there. It is because it's basically washing out the projection or the image that's being projected, because I want directional lighting at the front. So this way, the light goes straight down and it's not going to spill over. Nope, that was not incorporated into the actual equipment. All right. So with all this done, any questions? Yes.
Can you go back to the page where you explained all the
Yep.
subsets?
You did this one?
Yeah. I'll take a picture.
It's being recorded. But if you want to have your own copy, I understand that. All right. So now we are ready to move into quantifiers. Okay, so we'll go into quantifiers. So quantifiers is in a different note here. So let me go back to the modules. And then we have to look for quantifiers. There we go. All right, so the first thing before I even start, okay, I have to say that in normal English, conversations, you have been using quantifiers quite a bit already. Okay, every time you say every, all, none, some, those are all quantifiers. So I'm just making a statement that can be true or false. Okay, so do not try to take it as an implication of whether it's true or not. I'm just using it as an example. All professors at ARC sucks. Okay, so that's a quantifier, because as opposed to, okay, so it's useful to contrast all versus some. Okay, So if you think about the sentence of every professor at ARC sucks, that's one sentence, that's one statement, which may or may not be true. So I'm not interested in the truthfulness of that sentence. I'm only interested in the meaning of that statement. Whether it's true or not is irrelevant to me. And then the second sentence is some ARC professors suck. Okay, do you consider those two statements being different? They are different, okay? Because in the first one, if that statement is true, then someone can just self-identify and go like, I'm an ARC professor, and then the other person can immediately conclude, you suck. Right? But with the second sentence, you cannot infer because it only says some professors at ARC suck. But if somebody just say, yeah, I teach at ARC, you cannot automatically say, yeah, you suck. You may know somebody who sucks, but you may not suck. Is that okay? So it's important, and we intuitively have been using these quantifiers, throughout. I mean, since I don't know, 5 or 6 years old. Because I'm pretty sure 5-year-olds know how to use every. Or no, none. That's also a quantifier. All right, so knowing that, moving into quantifiers, I hope you guys feel a little bit more comfortable. So the first thing is quantifier implicitly apply to everything or nothing in the universe to make our discussion more concise. Let us use variable x to refer to a thing that we are examining, and p of x is some kind of Boolean function, also called a predicate, which we talked about already, applied to x. This means that depending on what x is, p of x is either true or false, or it returns either true or false. So are we okay with this entire paragraph here? Which is really just re-explaining what is a predicate, p of x, and x is a variable that will help us focus on. So what exactly are we examining right now? Okay, is that okay? All right. So to say that everything in the universe makes p of x true, we use the following expression. For all x, p of x, and without saying p of x is true, it is implicit that p of x is true. Is that okay? I don't know what that p of x is, but it applies to everything in the universe. Everything in the universe makes p of x true. Yep.
That upside down A is basically.
Yes. So the upside down A is the for all symbol. And once again, if you go to show math as and then go to the text command, it is / for all as one single word. That's how you enter that in LaTeX format. Okay. And then the next paragraph is just repeating what I said earlier. It's literally just saying for all x in the universe, p of x as a predicate is true. Are we good? So the other one is there exists, which corresponds to some. So in the other case, we have, for some x in the universe, p of x is true. The more formal way to say this is there exists x in the universe such that p of x is true. So the E that is in the reverse direction is exists, there exists. But if you do not prefer that phrase, there exists, blah, 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 you can always say for some. Okay, you can always change the symbol to for some x in the universe, p of x is true. Is that okay so far? All right. So with that said, we can now use quantifiers. So the quantifiers is basically saying, what if you negate there exists? So let me hide the answer to this particular question. So the question is there another way to say it is not the case that for some x, p of x is true? And once again, for some x in the entire universe, okay? So x can be an integer, can be a name, can be a person, can be a cat, can be a particular bacterium. can be, it can be anything, okay? But the question is there another way to say this? Okay, can I convert this somehow into a for all? So let's think about this one more time. It is saying it is not the case that for some x in the entire universe, P of x is true. So it can be converted into the other one, into a for all. Okay, so this is the answer. This basically means if I say it is not the case, which is the negation operator, for some x in the entire universe, P of x is true, isn't that saying the same thing that nothing in the universe makes P of x true?
So is it for all things it's false?
For all things, P of x is false. Or you can also say for all things, it is not the case that P of x is true.
So what's the difference between negating inverse A or inverse B? That's what it is. What will be the difference?
What is the difference between those two?
Negate A or E, yeah.
Between, say that one more time?
Inverse A, which means of, and then the E symbol.
So I think that's the two ways that you're writing it. What's the difference between them?
You mean between this one and this one here? Is that what you're asking? Okay.
No, I think you would think for all and for some.
Right. So this is, okay, if you think about it from the perspective of programming, okay, so I think that's probably a better way to do it. So let me see if I can present it after I talk about the equivalency between these two expressions. Do we all see that these two expressions are the same? So once again, I know these symbols is probably new to, I would say, 90% of this class. So it's important that we use it so that we get used to it. That doesn't sound good. So that we practice so that we get used to it. Does that make sense? And that's what I'm trying to do. So I'm consistently trying to use the same symbols, in all of the text here so that we get used to these things. And although there are things that I invent for some of my classes, such as the processor in CISP440, these are not, okay? These are mathematical symbols that are pretty much universal in math classes, as well as descriptions of algorithms. So that's why this is really kind of important. It is not the case that I can find something in the entire universe that makes P of x true. It's exactly the same thing as saying everything in the universe, for everything in the universe, there's nothing that can make P of x true. That's exactly the same. Okay, so now I'm going to transition to a code programming way of looking at for all and there exist. Okay, so you're going to say, so I'm going to write some programs here. And once again, this is not a programming class, so you really do not need to know how to write this. Okay, so we have I'm going to write the code in JavaScript because JavaScript does have the concept of a set. So this one here is going to be for all. So I'm going to define the function, and so we say here for all, and then we have a predicate function, which is P. So now we specify the body of this, and I'm going to say for this is all in JavaScript code. Let x remember, is it in or is it of? I think it is of universe. And I'm going to do some code here. But before that, I need to use a local variable. I'm going to call this result or answer. And by default, it is true. Okay, this is also important. So for each item in the universe, I'm going to say result is result and P of x. And then the function in the end just returns result. That's it. And I will scroll a little bit here. You guys can focus on the right-hand side again. And because the left-hand side, you know, has some coding thing that you need to pay attention to. All right, so in this particular coding example, I am I'm defining a function. So the sub thing is basically defining a function. The function is called for all. It requires only one single parameter, which is a callback. Okay, it's a function. P is a function itself. The result is a local variable, so you can kind of look at that as bool, result equals to false in C++. And then we have a loop here, which does not exist in C++. Because C++ for loop can only iterate, based on the three things that you give it, right? The initialization, the condition, and the post condition. But because this is in JavaScript, there's a way for me to iterate through a set. And universe is a set. So basically, for each iteration in this for loop, it's picking up a particular item from the universe and say, let's just examine this item in the universe for each iteration. Is that concept okay in terms of the control structure of this construct? Okay. So what do we do when we look at one particular item in the entire universe? We just say, well, result that thing here, but that was initialized to true is true and P of X. P, once again, is the predicate that we pass into the function. And we are basically just saying, let's apply predicate P to this X here that we're examining. And whatever it is, we're going to use a conjunction and with result and then put it back into result. Is that okay? And then when this is all done, which is obviously going to take a long time because we are looking at everything in the universe. But when this is all done, result is what we return. That's the value of the expression of for all blah blah blah. Okay. Are we doing okay so far with this example? So I'll give you a summary of what this says. It is basically saying if at least one thing is going to give me a false when we evaluate predicate P, the result is going to be false. All right. So now we're going to look at exist, okay? And I'm going to do some copy and pasting here. I'm not sure whether that's going to work, but we'll give it a try. No, it does not work. Okay. 6, 8, 11. All right. There we go. All right, so I'm just being lazy here and I'm just copying the structure. So this one is for each for exist. Okay. And the changes are very minor. Okay, so this one starts with a false and the conjunction becomes a disjunction. That's it. So we can now see, how for all is very closely related to their exist. Okay, so let me just kind of go through this also. So if you're dealing with their exist, okay, with the inverted E thing symbol, the default is false, unless I find evidence that at least one thing in the entire universe is making the predicate P true. But once result becomes true, it cannot become false again. Because every single time we attempt to change result, it is done using a disjunction. If one side of the disjunction is true already, it's guaranteed true. So is that helping you understand the concept? Because I'm trying to use something that you are familiar with. I know it's not JavaScript, but the concept of for loop is, it's a for loop. So I'm just trying to translate the mathematical concept into a programming equivalence of the mathematical concept. Is that okay? Yep.
What would let X of universe be in C?
There's no such thing as universe, because universe is a theoretical global variable that is a set that has everything in the entire universe. So it's just a theoretical thing. So I know many of you are thinking, 5 minutes left. So many of you are thinking, why do I care about a predicate being applied to my car or my pet or the germs that are surrounding me. You're absolutely right. We don't really care. So that means, we somehow need to have a way to filter and say, we only care about these numbers here, or we only care about those prime numbers over there. We only care about these integers over here. So we need a filtering mechanism. So the filtering mechanism is also, kind of denoted here. So this part here talks about the filtering. So the filtering basically, I'm going to use this as a filtering mechanism. In other words, let's just say that of everything, of all the things in the entire universe, I'm only interested in the things in the set X. Okay, which may only have like 2 elements or 3 elements. Okay, a very small, tiny little subset of everything in the universe. But that's the only thing I really care. So in order to filter out everything else, this is how I do it. So for all E, if you just focus on this for all E, it is still applied to everything in the entire universe. So by the time we get to the parenthesized expression, E can be your car, E can be your pet, E can be yourself. It doesn't have to be something that you're really interested in. But I'm using the implication here as a filtering mechanism. How does that work? What if E, okay, let's just give X a specific example. Okay, so let's just say that X consists of 1, 3, and 5 as integers. Okay, just 3 integers. Is that okay? And so now E is, let's say E is, what we're focusing on right now is the whiteboard eraser that I'm holding. Okay, this is E. So the first thing to ask is that whiteboard eraser an element of the set of 1, 3, and 5? You tell me. No. Nope. Okay. So if the left-hand side of the implication is false, what happens to the implication itself? It's true. It's going to be true. So that means in the loop that we are talking about, okay, so let me switch back to the loop here. So in the loop that we are talking about, when X is bound, okay, we use that word, when X is representing the dry board eraser, it is not, it is P of X is going to be true. Because P of X here is basically the same thing as this, the entire implication expression here. The entire expression within the parentheses right after the for all is P. That is your predicate. Is that okay? So when E is the dry board eraser and X as a set is 1, 3, and 5, the element of expression is going to be turned false. But if the left-hand side of the implication is false, the implication itself is true. As a result, that iteration of that loop is just going through like, yeah, we don't care about this. Yep.
What is it? What is it?
It's filtering so that we don't pay attention to anything other than elements of X. So for everything that is outside of X, that is not a part of X, we just say, yeah, you're just going to return true. Because we don't care about it. Does that make sense? All right. What if X, what if E binds to 3 as an integer? So just kind of imagine this E here is 3 and X is 1, 3, 5. Then 3 is an element of 1, 3, 5 is going to be true. So now we have the left-hand side of the implication being true. But now we cannot just say it's going to be true because there are 2 possible outcomes when the left-hand side of the implication is true, because now the value of the implication depends solely on the right-hand side. So now we really pay attention to P of E. It's like, is P of E true? Because in that case, the implication is true. On the other hand, if P of E is false, that makes the entire quantified expression false, because I find at least one example where P of E is false. So this is a filtering mechanism, which basically means for everything that is not in the set X, I don't care. It's not going to impact the default value of the for all. But when we're dealing with things that are inside the set of X, Now we really have to pay attention. So this is why I call that a filtering mechanism. So the shorthand of doing this is explained here. I thought there was another one. I don't remember where I put it. All right, so I'm just going to put it in here. Okay, so I know we're running out of time, so I'm just going to put this up here. So I'll just say, for all x such that p e in x implies p e. This is the same thing as for all e in x p. So it's just a notation difference. I personally like the second notation better, so we can use the filtering mechanism before we get to the actual thing that we care about, as opposed to putting the filtering mechanism within the parentheses after the for all. So they mean the same thing. This is just a notational, shorthand thing that I prefer to use. All that I'm saving in the end is I don't need to write the implication operator here. This one does not have an implication operator, but I think the second form is more clear, but they really mean exactly the same thing. All right, so your reading assignment before next Monday is going to be finishing up the entire quantification or quantifier module and also getting back to the set notation, but using quantifiers this time. If you still have time over the weekend, you can get started with functions, okay? Because that depends on all the notations that we have been talking about. Yeah.
So over this, I came in late, so we just focused on that, the basic stuff.
It's a false relevant. This is not equal to this. This is kind of like this. You use it very, very, very. All right, it's not exactly, but it's like 99%.
What is the thing? This is saying.
No, the gate sum of x. So another thing. It says in no case is p of x